Welcome, everyone. Thank you for joining us today. We are very excited and happy to have you join our 8th and last Morocco AI webinar of this 2022 AI webinar series. So let's give a brief intro about Morocco AI and who we are. We are an initiative led by AI experts in Morocco and abroad. These experts are professors, researchers, and AI professionals. Our main mission is to promote AI growth in Morocco and build a strong collaborative AI community, both locally and abroad. We have launched different activities such as AI webinars series, where we aim to invite AI researchers to present and share their work with the community. You can rewatch previous webinars on Morocco AI website or YouTube channel. And for today's webinars, I will be your host. I am Iman Khouja. I am currently data scientist and also Women Tech ambassador. And don't forget to follow us on LinkedIn, Twitter, and Facebook, and join our community on Slack to be notified about our upcoming events and conference announcements. In the last webinar of 2022, Dr. Mehdi Cherti will be presenting an open large-scale dataset for training next-generation image text models, where Dr. Mehdi will be presenting his accepted work at NeurIP's 2022 dataset track. Dr. Mehdi received his PhD in machine learning from University Paris-Calais in 2018. He is currently a postdoc at Jülich Supercomputing Center within the Scalable Learning and Multi-Purpose AI Lab. His research focuses on deep generative models and how to use them to learn representations that can help to design novel and useful objects. He is also part of the LINE team, a nonprofit organization that focuses on studying and developing large-scale machine learning models and datasets and making them fully available to the general public. If you have any questions during the presentation, please type them on the chat on Zoom or YouTube, and I will make sure to ask them at the end of the presentation. And please be sure to stick around for our networking session right after the presentation, where we'll break out in smaller rooms so you get to meet each other. The presentation will last for approximately 30 minutes, followed by 10 minutes Q&As. And without further ado, Dr. Mehdi, please, the floor is yours.
Thanks, Iman, for introduction. Thanks a lot for inviting me. I'm very happy to present my work to the Moroccan AI community. So yeah, I will share my screen now. I think it works, right?
Yes, we can see your screen.
Okay, great.
Perfect.
So yeah. So as Iman mentioned, so I will present some of my recent work I've been doing with my collaborators and colleagues. So Line 5B, which will appear in NeurIPS, it will be presented in around 2 weeks, actually. So I will start with some context and motivation. So I'm quite sure you have seen some of the quite impressive advances in image text models in general, text-to-image generation models in particular. So this is an example from OpenAI's DALL-E 2 generative model, where they train the model on text-to-image generation. So here, basically the model take as input a text, any description of an image that you want to generate, and it generates a higher resolution, like 1K by 1K in this example, image corresponding to the description. So they trained this model on so the model is 5.5 billion parameters, trained on a dataset, a quite large dataset of 650 million image text pairs that they collected from the web. So it's a private unreleased dataset that they use. So another impressive advance that we have seen in the last 2 years is a CLIP, which stands for contrastive language image pre-training. So CLIP have been shown to lead to very strong image representations. So basically in CLIP, you have a text encoder and an image encoder. And so the text encoder takes as input text and converts it, predicts text representation in the form of a vector. You also have an image encoder, which takes as input an image and predicts an image representation in the form of a vector of the same size as the text representation. So the goal of a clip is to train the image encoder and the text encoder to make the text and image representations close together for image text pairs from the dataset. So you make, like more concretely, you make the cosine distance very small for image pairs that correspond to each other, image text pairs that correspond to each other. And for unrelated image text pairs, basically negative examples, you make image text pairs cosine distance as high as possible. So basically what the model is trying to do is trying to find optimize the model parameter to find which caption belongs to which image based on the learned representation. So using this simple objective and scale to a large data set of 400 million image text pairs, so again from a private data set they collected, the model can learn very strong image representations as shown here. So this is a common theme in deep learning. First, you have a pre-training phase. So you pre-train your model on usually a large data set to learn like a generic representations. Then you have the transfer phase where you specialize your model for tasks that you care about. So here, when you pre-train the model, you can test it on a few downstream tasks, and they show here the performance of the model on like here it's an average of 27 data sets, and they compare it to prior models trained in a supervised way with labeled data, and they show better results. What is more remarkable about these models is that they have zero-shot capabilities. So, this means zero-shot capability is a way to use models for any classification task. So you can apply them basically for any classification task using only class descriptions, and no labels are needed. So, or no annotated labels like supervised classification. So how they do that? So once you pre-train the model, you get a text encoder and an image encoder, and let's say you get a new classification task that you want to solve. So you have your class names like plane, car, dog, and so on, and you can construct prompts. So what they call prompts, which are basically descriptions of the classes. So it can be as simple as a photo of the class name. So a photo of a plane, a photo of a car, and so on. So for each class, you compute a representation using the text encoder, a photo of a car, a photo of a plane, and so on. And let's say you have an image you want to predict which class it belongs to. So you just use the image encoder, you get the image representation, and you try to find which class is the closest in cosine distance in terms of cosine distance to the image representation. So this way you can predict using zero-shot for any classification task. So what they show here, like compared to prior works, a massive improvement. So this is quite huge. So this is a result on ImageNet, which is a very common data set used to evaluate the models in vision. So in prior works for zero-shot, you see this massive improvement. So this is percentage of accuracy. So yeah, minimum is 0, max is 100, and yeah, there is a quite big gap. What's also remarkable is that this 76% accuracy is equivalent to a model trained on, in this case, a convolutional model trained on 1 million examples from ImageNet. So you get the same accuracy as a model trained on 1 million examples, but without using any labeled data. So this is quite impressive. They also show that the model is robust to distribution shift. So here, for instance, to evaluate distribution shift, people have designed different versions of ImageNet. So in ImageNet, you have different image categories, and like real-world pictures of different categories, like here. And people constructed a different version with the same classes, like here, ImageNet Sketch, which is basically like ImageNet, but with sketches, like illustrations. So when you train a supervised model using ImageNet and you evaluate it on Sketch, you get a very small accuracy. The same thing if you do it with zero-shot clip, so you get so similar accuracy as I have shown before. But when you apply it on Sketch, you don't lose so much. So there's quite a big difference. So also other different datasets that are used for evaluating robustness to distribution shift. So results have been improving further since CLIP. So a lot of papers used larger datasets. So CLIP was 400 million. Other subsequent works used large datasets, larger models. So Align used around 2 billion image text pairs, but Basic around 6.6 billion, and so on. So the trend is about improving accuracy by using larger models and larger datasets. So as you have seen here, none of these large datasets have been released publicly, which make it very hard to train and study these models at large scale and improve them, especially in the academic setting where it's quite difficult to train these models. So so we propose Line 5B. It's a completely open dataset of around 5.8 billion image text pairs filtered from Common Crow. So some statistics. So it's around 40% of images with English captions. So the rest is other languages. So here, a frequency of top 10 languages in the dataset. And here, a comparison with public datasets. So we have different datasets that are available. And Line 5B, in the English subset, we have 2.3 billion image text pairs, and it's quite large compared to the publicly available. So it's about more than 20 times larger. And so here are the private datasets here. So we provide another detail here is that the dataset is filtered from Common Crow. So Common Crow is basically an archive of the web. So you get HTML web pages, and you can. So the way you construct the dataset is you get like EMJ tags with alt, so this alternative attributes, which usually contain text describing the image. So most of the descriptions are quite irrelevant, very noisy. So what we do is we filter Common Crow to have reasonable text-image alignment. So you do that using CLIP, actually. So models released from OpenAI so basically, we use the text encoder, image encoder to compute representations. So once we download an image and its corresponding text, we compute their text and image representations. We compute then the cosine distance, and we threshold it. So if it's above some fixed threshold that we choose, then we keep the pair. Otherwise, we filter it. So we provide a different set of tools. So not only the dataset, but also tools around it to use it and download it and make subsets from the dataset. So so just to have an idea, the full dataset needs 220 terabytes of storage if you want to download it. So the metadata needs around 2.5 65 terabytes. So in the metadata, we provide the URL of the image, the corresponding caption, the clip cosine similarity, two non-safe for work score and watermark score using some models we trained. We also provide a tool called clip retrieval. So this tool you can, I have to mention, the image to dataset tool was made by Romain Beaumont, which is one of the authors of the paper. Same as clip retrieval. So clip retrieval is a user interface that people can use to explore the dataset. So it's powered by clip actually. So you can type an image description with text, and you can get corresponding images. So it's basically like a search engine on using the dataset. Some projects that are using Line 5B. So we have so actually you don't need to download the full dataset to be able to use it. Some people have been working on subset generation. So this is one of the use cases of Line 5B. So one subset that people worked on is line high resolution. So it's a 70 million subset for training super resolution models. So it's high resolution images only, and can be used, for instance, in generative models if you want some high quality images. Line aesthetic, it's a subset of 120 million aesthetic images. So so people use a model trained on human ratings of pictures. So basically you get ratings, you train a model to predict ratings, and you use this model to filter the images for aestheticness or a proxy of aestheticness based on human ratings. Another project which is very notable is probably lots of people have heard of it, is Stable Diffusion. So Stable Diffusion is a text-to-image generative model similar to DALL-E 2 from OpenAI. And so people trained text-to-image latent diffusion model on 512 by 512 resolution using those subsets that I mentioned before. Yeah. So I will now go into the part which I have been most involved in. But so this is a part where we try to validate the utility of the dataset by reproducing OpenAI's clip models. So we train different architectures. So this is our architecture sizes and hyperparameters. So number of parameters here. So we go from 150 million to 400 million around. And yeah, just to have an idea of how much resource intensive these models are. So number of GPUs here used are up to 400. So NVIDIA, so we use NVIDIA A100 GPUs. And these models require quite high batch sizes, so on the order of 30,000, 40,000. In terms of training time, so we go up to so depending on the model, we can go from a few days to 1 week in the largest model that is shown here. Yeah, so to train these models, we use supercomputers. One is Jülich Booster from Jülich Supercomputing Center, where I work on. So it contains around 4,000 NVIDIA N100 GPU and Stability AI AWS-based supercomputer, which currently has around 5,400 NVIDIA A100 GPUs. Okay, so before going into the details of the results of pre-production, I will make a quick digression into neural scale laws, because I think it's quite relevant to the topic. So in 2020, Kaplan and al. Tried to study the performance of neural networks as we increase the scale. So scale here can be considered in different axes. So number of parameters, like we increase model size, dataset size, we increase the dataset size, and compute. So basically the number of total compute that is spent for training in terms of, for instance, floating point operations. So what they observe in this work is that, so here for when you, so the relationship between scale and model performance follows a Poor law form, which shows up as a line in a log space of x and y axis. So this is quite remarkable, that the performance of the models is very predictable with scale, and it has been shown in different settings. So like in this picture here, in this figure, we have number of parameters in the x-axis, and the y-axis we have test loss. So this is a model trained on language modeling, so a bit like GPT-3, if you are familiar. So what you do here is you vary. So yeah, one thing I have to mention. So the model, the relationship follows a Poor law form when there is no bottleneck on the other. So when you vary one scale and you fix the other scales. So here, for instance, you vary the number of parameters, and you make the dataset size and the compute as big as possible, as big as you can, so that there is no bottleneck. So when you do that, and you train different models with different parameters, and you do the fit, you get a quite predictable performance with scale. And this goes on different orders of magnitudes. So you can see it here. So you can do the same for dataset size. You can grow the dataset size and make the model parameters as big as you can, the training compute as big as you can. And again, you see a Poor law form. For compute is a bit different. So for each compute budget, so you fix the compute budget, and you train different model sizes that correspond to that compute budget. And you just keep the best possible model. So these are the different models shown here, and you just keep the best, like the frontier, the best model for each compute budget. And you get again a Poor law form. So implications of this neural scale laws is that first, you can extrapolate model performance on larger scale. So if you have like a Poor law, you can use it to predict the performance on larger scale. You can compute optimal model size for a given compute budget. So let's say you have a fixed compute budget. You can figure out what's the optimal model size that you should use. You can also compare different scaling curves of different architectures, pre-training datasets, and losses. So yeah, so depending on the architecture or the dataset that you choose for pre-training, you can have different scaling behavior. So here, for instance, they compare one of the works. They compare like a convolutional model with a transformer, and you can see that the transformer scales better. Yeah. So what I've shown before is that they studied. So the work I've talked about before study the performance of test loss, but it also worked for downstream transfer. So multiple works came after showed this. So not only for test loss, but also for downstream transfer, which means, so basically the tasks that you care about. You pre-train a model, and then you evaluate its performance on downstream tasks. So using, for instance, you can take, for instance, you can fine-tune the model on your task, or you can train a linear classifier on the top of the representations. So again, you find a poor law form here. So here you have compute axis for compute for x-axis, and accuracy, well, here is error rate for y-axis on downstream tasks. Here it's not strictly a poor law. It's basically a saturating version of poor law. You see some saturation starting here on both ends, but it's basically in the middle, it's a poor law. Yeah, so going back to CLIP, so we train different model sizes. So here are model sizes growing by a number of parameters. We also consider two dataset sizes, 400 million and 2 billion from Lion. So 400 million data scale and 2 billion. And this is what you evaluate on. So we collect a set of 25 tasks we call Vita Plus, on which we evaluate the models with zero-shot classification, like I described before. So this is just the details on the different tasks we evaluate the models on. And this is what you obtain. So similar to what have been shown in neuroscale laws, we can see, so this is again a log scale in X and Y axis. We have compute, total compute, and we have accuracy. And when we do, when we show, when we plot the results in a log space, it fits very well in a line again. So this is an ImageNet. This is zero-shot classification on ImageNet, and this is zero-shot classification on Vita Plus, which is basically an average over 35 tasks. So yeah, similar to what have been shown before, we see this relationship between compute, total compute, and accuracy on downstream transfer. Yeah, so here is just more details. So I will not go to all the details in this table, but just two conclusions from the results. So here we have different downstream tasks in the columns, and we have model sizes. So here we have bigger and bigger model sizes. And here we compare with CLIP from OpenAI. So this is CLIP from OpenAI. What we see is that, so one first conclusion is on the smallest model scale, so this B32, we see quite similar or better results on Lion. So yeah, so quite small differences in ImageNet. So this is ImageNet, and yeah, depending on the dataset, is either a bit better or a bit worse, but in general better. Whereas where we go to the largest scale of the model, we see differences. So between Lion and OpenAI's CLIP. So here OpenAI's CLIP has better results. So we see here a bit smaller accuracies. And yeah, so we have different hypotheses, which I can talk about later. But yeah, this is something we are investigating. Second conclusion is that with larger data scale, we get better results. So here, the same B32 model when we train it on line 2B, so instead of line 400M, we basically get better results everywhere. Yeah, so here is just a different view of the results. So we have, here is just to show the importance of data scale. So this is sample scene, basically the number of training iterations that you allocate for training. And what we here we compare performance of the model when training on line 400M, 400 million, compared to line 2B, 2 billion images. So if we only use an intermediate amount of training compute, we see that the difference between the two is quite small. So they are quite the same. We can only start to see the differences when we don't have when we have less bottleneck in the compute. So we see the difference between line 400M and line 2B only when we train for long enough, basically. So when we train for long enough, we get a better result with line 2B. So this is with the smallest model scale, the B32, but also we see the same for L14, which is the largest one. So if we just train for an intermediate amount of compute, we get similar accuracies, but we can only see the differences when we train for longer. Yeah. So so these are other results on zero-shot retrieval. So zero-shot retrieval is a task where you try to basically, for each image, try to find the corresponding captions, and also for each caption, try to find the corresponding image. So yeah, this is the metric we use is called the recall at different levels. Yeah, I can go also to more details if I have any question about that. But basically, when we evaluate the model on the models on zero-shot retrieval, which means we use here a dataset called COCO to evaluate retrieval without training. So this without fine-tuning the model on this specific task, hence the term zero-shot. We see in general quite systematically better results with lion models. So here, yeah, it's really depends. As you can see, it really depends on the task. So for zero-shot classification, we saw some differences, whereas for retrieval, we see quite systematically lion gets better results. So here, this is the original clip compared to lion models. And yeah, again, original clip. So here, basically, we get, in general, better results. Yeah. So yeah, so that's it for today. So I just put here some links if you are more, if you are interested in exploring the dataset or contributing or just checking the results. Yeah, so I put also here the link for our Lion Discord server if you are interested in improving the dataset, working on different projects. So we are very happy to include collaborators. Yeah, thank you for listening.
Thank you, Dr. Mehdi, for the great presentation and also the great content about generative models. So it looks like we have here some few questions. I will start with the first one. Okay, so we have a question from a participant. He is asking if you know any works that are creating big data sets for text to image in Arabic.
In text to image, well, I'm not quite sure. I don't. Not aware of any working on Arabic. So in Lion, So in Lion you will probably not find much Arabic, uh, especially that our filtering model is trained on English. So it probably won't work uh, for Arabic. Yeah,
Okay.
so I'm not aware of any people working on that. It will be actually great. Yeah.
Okay, so
As a
also for
contribution.
other languages, do we have any data sets like French or
So sorry
German?
again.
And for other languages such as French, do we have some work that creates a big data sets for text to
Yeah.
image?
So I have to mention one thing. So some people are working actually right now on a multilingual clip.
Okay.
So basically, what you can do is uh, take a pre-trained text encoder that has been trained on multilingual data and fine-tune it on Lion, for instance. So that's possible as well.
Okay, thank you. Thank you for this clarification. We have another question from Yasmin. She is asking when should we use CLIP instead of other generative models such as DALI or Stable Diffusion?
So one thing I have to mention, so CLIP is not strictly a generative model. So CLIP is basically only giving you an image and text representation. Of course, we can use it for guiding. So it has been used in several works for guiding image generation. So probably some people have are familiar with VQGAN plus CLIP, where people. So it was a bit before DALI 2, I think after DALI 1. So people tried, so when OpenAI released CLIP, people started to use CLIP to guide image generation. So you start with a random image and try to use CLIP to make an image uh, um, uh, close to the text that you want for describing the content of the image. So the question was, when should we use CLIP?
Use,
Yeah,
yeah,
So they
exactly.
have different use cases. So CLIP is more like a model that can be used for prediction, I would say, and for retrieval. So if you want to use the model for classification or for retrieval, so CLIP is a is perfect for that. DALI and other similar models are for generation. Uh, text to image basically, or in painting. Some people use them for in painting. So you mask some part of the image and you try to recover it, also with conditioned on text. Yeah.
Yeah, thank you for your answer, Dr. Mehdi. So I have here another question. It's more about the names of the models that we have that you had in your presentation, such as B slash
Yeah.
32. Or could you please explain this to us more?
Yeah, sure. So this is vision transformers. So these are just names that have been chosen for describing the model size. So B is base, L is large. So here we only have B and L. Yeah, so B is base, L is large, and 32 is patch size. So this vision transformers, maybe it's better if I find a figure. Yeah, maybe I can look at it here. Vision transformer. Yeah, so that's perfect. So in a vision transformer, you divide your image into patches. So you get an image, you divide it into patches, and the 16 is basically the patch size. Yeah, so that's it, the 16. And well, it was what, 32 and 16, yeah, and 14. So this is describing the patch size.
Okay, thank you. Yeah, it sheds light on this. Thank you very much. We have another question from Hassan. He is asking that such models demands a lot of computational power. Could we train them on our phones, or we can only deploy them on our phones?
Yeah, it's to pre-train them on our phones. That's, I would say, quite difficult for now. So the advantage of such models is that they can be they are quite fast at inference. And actually, so here, let me go back to zero shot. Yeah. So once you train the model, you don't need to train it anymore. I mean, the model will at some point have some task where it will not perform well, but like for tasks that it can support, you can just use it as is without training. So if you want to use it on your phone, you can use stuff like zero shot. So you just you have a classification task, you just encode your tasks, you encode your classes, and just basically you have a classifier without training. So that's the big advantage of such models.
Yeah, it makes sense.
There are also people also work on distillation. So distillation is a way to reduce the size of the models. So you can use you can train a smaller model to imitate a bigger model on some specific task, for instance. And yeah, usually you can make the model much smaller, and that could fit on a smartphone. So there are a lot of works on distillation and reducing model size difference. Yeah.
Yeah, they require a lot of computing power. So we have here a question from Redwan. He is asking, do you think the advancements are more driven by algorithms or by the large amount of data plus the big computing power?
Yeah, I mean, I would say it's a mix. So in Clip, for instance, I mean, yeah, I mean, in a lot of cases, I mean, in some sense, the objective function using Clip is not something really novel. You can only see you can only see that you get a strong representation and performance on downstream transfer when you scale to larger datasets. So yeah, I mean, so it's a mix, I would say, still. You also get some algorithmic advancements. So for instance, in diffusion models, yeah, of course, you need to train on large models and large datasets, but also the diffusion model architecture is quite, and loss function is quite, was quite an advancement itself. So it's algorithmic and also scaling.
Okay, so it's a mix. Yeah, thank you for your answer. We have another question. It's about a participant who is asking, Are diffusion models now the state of the art over GANs?
Yeah, so currently, diffusion models have the best quality as far as I know in terms of generative models. The downside is that they are much slower. So this is they are much slower for generation. So you have to in diffusion models you have to iterate. You have to apply many forward passes to generate an image, whereas in GANs usually you just have one step, one forward pass. It's milliseconds, depending on the model side. And people also have been working on mixing a bit the two approaches. So there have been one recent paper from NVIDIA, like taking the advantages of each. So the paper is called denoise in diffusion GANs. So basically a mix of the two, denoise in diffusion GANs. So it's at the same time quite good in generation and quite fast. But as far as I know, it has not been scaled to large data sets. So it's quite limited to small data sets so far.
Okay.
Yeah, fast sampling, high quality samples, mode coverage, diversity. This is what they're trying to, basically mix the two.
Okay, so thank you for sharing with us the paper. And for sake of time, we will wrap up the Q&A session with this question that resumes two questions. It's about the context of Morocco, on how can we use pre-train those model with limited resources, such the case that we have in Morocco, where we require large amount of computing power.
Yeah, so there I would say that's where pre-training can help. So usually when you have limited resources in terms of data, what you want to do is pre-training on a large data set and fine-tune it. So instead of training from scratch. So in this case, we can start from a pre-trained model. Let's say, let's take for instance the text encoder part. We can start from a generic model pre-trained on web data, then fine-tuning data also scraped from the web, but with Arabic, for instance. That's one way to go.
Okay, thank you for answer. I think that your answer will be helpful to the participants. So it looks like we covered the majority of the questions. We still have some, and I invite the participants to join us in the Ask Me Anything to Dr. Mehdi room to ask the remaining questions. So first, I will just stop the streaming live, and then we can move on to the breakout session.